Well, hello again everybody, and welcome to part 3 of our Regent Tone battery eliminator restoration video. So in last week's episode we did manage to actually rescue these old 1920s transformers and graft some new wires onto it and made some measurements of the transformer's efficiency. And as we found, these aren't particularly efficient as they go, especially compared by modern standards, but I'm sure they're actually quite good enough to work in this battery eliminator. So we're actually going to be taking a closer look at some of the other components in here this week. So what we've got planned is I'm going to take a look at this. This is a metal rectifier, and I think this is probably made by the Westinghouse company. So we're going to have a look at this metal rectifier, see if it still functions. And also we've got these large boxes here which have got capacitors inside them. Now I've got absolutely no doubt that the capacitors will be bad, and we're going to have to replace these. But before we actually go ahead and replace the capacitors, we're also just going to do some testing on them. I think they do have the capacitance values stamped on the outside of the box here. So what we'll do is we'll take some measurements on these, and then these capacitors are actually potted in what I think is pitch or tar. And so what we're going to do is we're going to take these into the garage and I'm going to put them under the heat gun, and hopefully we can actually get the tar hot enough so we can actually tip out the old capacitors and maybe have a cut into them, have a closer look and see how they're constructed. Now the final thing that I need to have a look at is, again, in part 1 of the video we found that we've got this potentiometer control, and unfortunately what I found is it appeared to be open circuit, this potentiometer. Now it could actually also be that the connections are just so dirty that I wasn't able to make contact on them, but I think that I do need to strip this potentiometer down and have a look inside it. And again, as we said last time, it is a little bit unusual because rather than just winding, rather than just spinning, now you can see that the knob turns, but interestingly as it turns the knob actually winds in and out, and I've never seen a potentiometer like that before. So it'll be interesting again to take a look inside and see how this thing's constructed. Now unfortunately we've got the usual problem that the knob here is actually retained by a little screw. It's a little flat-headed screw, and at some point in the past the previous owner has probably also tried to remove this knob and is broken off. I can actually see one side of the slotted screw is actually broken off, so although I've tried to put a screwdriver in it and turn it, that didn't work. I've been dribbling WD-40 into it for a week, again trying to loosen it, that didn't work. So again I think we're going to be forced with having to drill this out, which is always a bit of a perilous exercise, but I think we've got no choice, so maybe we've got to drill that out. We'll do that in the garage today as well. But what I'm going to do first is actually just dismantle it. So reaching for the universal nut buggerer, I'm sure we can use this to get them out. So there's our metal rectifier liberated from the chassis. We'll take a close look at that later. Let's also do a little bit more snippy snip snip. I'm also going to remove this back panel to make it easier to clean, but I think I'll start off by removing this little connector block here, which is actually used to select the primary voltage tapping on the transformer. So let's just liberate that. And I think if I remove this screw, the whole back panel should come off now. Not sure what that's made out of. Okay, magnet sticks to it, so it seems to be made out of steel, which looks as though it's been coated, or certainly coated with something shiny. I don't know if that's brass or copper. Kind of almost looks more of a coppery colour than brass, but I don't think that'll clean up particularly well, because again it feels as though it's actually lost its plating. But yeah, we'll give that a go, see if we can clean it up. Okay, that's the wires disconnected from these capacitor banks. Hopefully we can now take the capacitors out. Now for whatever reason it does appear that a lot of old radios, the actual slots on the screws are actually very, very narrow. They're actually much narrower than a modern screw. So I have a screwdriver which I just use for old radios, which is effectively, you know, just quite a bit sharper at the end than a normal screwdriver. Well, as you can see, we've gone ahead and we've removed our capacitors from the chassis without any great difficulty. But one thing I actually did notice is that there's actually some holes drilled through the bottom of the capacitors, which were the mounting holes, and they almost look as though they were kind kind of holes were put in with a rusty nail or something. You know, they're barely round and they're slightly elongated. And I can only assume that this was actually manufactured. Again, it's just another sign that it was manufactured quite crudely, almost thrown together. So I suspect that this unit was actually, you know, somewhat built down to a price. As you can see, we've actually got two sizes of capacitors here. They are physically different sizes. We've got a larger one and a smaller one, and it's got written on the side of it here, the brand is TCC. They're both manufactured by TCC. This one says 6.5 MF, which I think was that millifarad, which I think is the same as microfarad, but yeah, they would be about 6.5 microfarad, and this one says 4.5 microfarad on it. The only thing I'm not sure about it is they've got AF stamped on the bottom of them, A and F, and again A and F stamped on the bottom of this one. I can only assume that maybe the A and F refers to the fact there's maybe two capacitors in them. I'm not exactly sure. Now certainly there's quite a lot of different terminals on here, which would lead you to believe that there is more than one capacitor inside these pitch blocks. What we are going to do is we're going to melt the pitch out of them and find out, but before we actually do that and destroy them, I thought we could just take some measurements on them. But I can see that some of the terminals appear to be linked together, so what I'm going to do is I am going to try to just open these links up. We'll just give that a bit of a tug, make sure I did imagine it. Oh no, I didn't imagine it. Oh, I wasn't expecting that. I was expecting these to put up more of a fight. Will that come out? You never know. Oh, I can actually see into here. Okay, so what we appear to have is a block of wax which has actually been capped off with some of this pitch covered material. I'm actually quite pleased with the way that that's come apart, because it does mean that we stand a chance of actually being able to just kind of put this back as it is, maybe just you know, temporarily just glue the pitch back on, even just so it still looks original. So that's quite good the way that one's come off. I guess we probably won't be that lucky with the other one. Anyway, we can actually see that it's actually revealed what I'm guessing is some paper capacitors which are covered in wax. Now the question is, are these paper capacitors any good or not? I don't know. I mean, I'm going to replace them anyway, because I certainly wouldn't trust them with a few 100 volts across them. But before we go ahead and put any power on them, let's try my digital meter on them. 4 microfarads, so that's probably what we would be expecting. I mean, it does say 6.5. Let's try one of the others. Again, that's measuring bang on 4 microfarads as well. That one's 3.8 microfarads. Is there another capacitor at the end? No, not sure about that. So it's actually coming up with some good capacitance readings there. Of course, we haven't tried to put any voltage across them. So the lowest voltage setting that my insulation resistance meter does is 250 volts, so that's what we're going to have to try it on. Okay, that's measuring dead short at 250. The next one's measuring dead short at 250. And the next one's measuring dead short at 250. Now, of course, I might be exceeding the rated voltage for these, because it doesn't say anything on them. It doesn't give me any idea what the rated voltage is. But to me, yeah, they are looking, they're not looking good then. I think what we might do with this second capacitor is, before I dive in with both feet and just dismantle it, I think what we'll do is we'll just check it for capacitance. So the first pair of terminals at this end are measuring 3.8. Second set of terminals are measuring 3.6. Let's just see what the set of terminals at the end are measuring. I think they're measuring effectively 1 nanofarad. So this material inside here, to me, this just feels like candle wax. In fact, I'm sure that's what it actually is. I think it is a candle wax material. This is going to get a bit messy on my bench, but we can always give it a clean. So taking a close look inside this capacitor, we can actually see why we were getting those different capacitance values. So we've got two big capacitors here, that one, and then physically this capacitor here is physically smaller. And of course, if the capacitor is physically smaller, it tends to be, if the voltage rating is the same, that means that the capacitance is going to be smaller. So I guess what we should have had here is we should have had 2 microfarads, and then this one at the bottom must have been the 0.5 microfarads to actually make up our 4.5. So I think that's probably what we've got. I wonder if we can take another measurement, or if I've actually damaged this. Let's take another measurement. Yep, 4 microfarads, 4 microfarads, well, 3.5 microfarads, and about 0.8 microfarads. So I do wonder if these capacitors were always slightly over the capacitance value that was stated on the tin, or if they've actually just gone high in value because they're actually starting to fail. Because that is one thing I have noticed, though, mainly with electrolytic capacitors, as they start to fail, what happens is they quite often go high in capacitance value. Now, I don't think these are electrolytic. I think before I explore any further, I'm just going to put some gloves on, because you never quite know what chemicals and what materials you're dealing with. So I'm going to do that. So as you can see, I might as well go ahead and go the full Shangu. So now I'm bagged up, we can go in. This might take a little bit of time, so I'll bring you back when it's all warmed up. Well, I think we're getting there. Okay, so there's one section of our capacitor out, and I think probably the other sections will come out somewhat easier now. Let's try that. And can we get the final one out? So there you go. So we've just got some wax in the bottom of the can, and we've got some reels of waxy paper with what looks like some stampings on them. So just to show you, we will actually go ahead and we will unwrap just one of these capacitors, because once you've seen one, you've seen enough. So what we need to do is we just need to cut into it. There you go. So in many ways not particularly exciting. So all we've actually got is we've got layers of aluminium foil here, and those layers of aluminium foil, they're actually just separated. They've got a piece of paper which is impregnated with probably oil or wax, or a combination of the two. So if you unwrap it, we just end up with like a long streamer of aluminium foil and paper. So I think you'd probably class this type of capacitor as a dry paper capacitor, as opposed to, you know, one of the more modern electrolytics we might find. And just as a small reminder of how things have changed, here's a 4.7 microfarad capacitor, because this one was 4.5. So this is 4.7 microfarad, and this one is rated at 450 volts. So I'm sure it has an actual higher voltage rating than this one, but yeah, just for comparison, things have changed quite a lot, haven't they, in the last 80 years? Well, you've already seen me removing the wax potting from one of these capacitors, so I think we don't need to look at that again. But what I'm doing is I'm just scraping away the top layer of wax, because I want to see if the construction is just the same. So this is just like the previous capacitor that we looked at, in that we've actually got 3 large wrappings of paper and foil here. So each one of these is going to be 2 microfarads. So that's going to be 2, 4, 6 microfarads. And then we've got a little wrapping at the end here, which is going to be our 0.5 microfarads. So there we go, there's our 6.5 microfarads. And it's interesting to see that it's actually manufactured in different banks of capacitances. Whereas I guess a modern capacitor like this is just one single long wrap of foil. They've actually split this up into different sections. I guess what they could do is, depending on what size of capacitor they were making, they could probably make it up of almost any value they wanted just by adding these 2 microfarad sections, so I wonder if they even made much longer capacitors for higher values of capacitance. I've salvaged one of our 2 microfarad sections from the bin, and I've gone ahead and I've soldered a couple of wires onto it because they were in danger of breaking off the top of our wax capacitor here. But I thought it might be interesting just to explore the leakage a little bit more. So I've got the Dairy meter, the DE5000, and I've also got a peak meter on the bench here. So let's just take a quick measurement of capacitance again. So you can see that the DE meter here is measuring 3.9, nearly 4 microfarads, whereas our peak meter here is reading considerably higher at 7.5 microfarads. So from that you may be wondering which of our meters here, the peak or the DR meter, which one is actually reading the capacitance value correctly. Well, they're actually both measuring it correctly and they're both measuring it wrongly. Just as an example, I've gone ahead and I've got a 2 microfarad, it's actually 2.2 microfarad capacitor rated at 250 volts, so we'll just do a sense check with this one. So this is kind of the model equivalent to our wax paper capacitor here. So this measures 2.28, and again just measuring the peak meter, and the peak meter measures 2.29. So our 2 capacitance meters do agree with each other when they're reading a modern capacitor. I say modern, this one is actually probably still from the 70s or 80s, it's an old polyester, but the readings do agree. But they certainly don't agree when we're measuring this wax capacitor. So you're probably wondering why, and the answer to that is because this capacitor, to put it simply, it's failing. What's happening? It's going resistive. So I've taken our capacitor here and we're just going to measure the resistance of it using the flute meter, and it's coming up as about 4.7 megohms. Now 4.7 megohms is far too low a resistance to be reading across a capacitor. Now I did a little bit of research online where I was looking into paper wax capacitors like this one, and it says that the minimum resistance that you should be able to measure is 1000 megohms. So you can see that this one is only coming up 4.7 megohms. So yeah, we've got some serious leakage going on here. And again, we'll just do the comparison with a modern capacitor. And what you'll find is the resistance increases rapidly and then it starts to slow down because you've got kind of an exponential curve for capacitor charging. 50. And this meter obviously reads up to about 50 megohms and then it's over range. But you can see there's pretty much no leakage across this capacitor. The only resistance that we were seeing was just a function of the capacitor charging up, whereas this capacitor was definitely demonstrating some resistance across the terminals. So we saw earlier that we had a piece of foil, then we have a piece of paper, and then we have another piece of foil. So it's actually that piece of paper that's breaking down. As I understand it, there's problems with the manufacturing of this paper, and the paper becomes acidic over a number of years, and that acidity leads to some kind of degradation of the material, and it makes it turn resistive. Now of course, using a benchtop ohm meter like this, we've only actually got probably just a few volts across the terminals of the capacitor. Well, I'm afraid things get considerably worse in terms of leakage the more voltage we put across it. So again, we could just show that using our megameter. So we're going to go ahead and I'm going to test this capacitor at the lowest voltage reading that this meter can read at, which is 250 volts. It does of course go up to 1000, but we're going to do it at 250. Switch on, and this is actually indicating a dead short 0.0.0 megohms. So yeah, this meter is seen as a dead short, this capacitor. It's always nice to have a comparison, so let's take our more modern capacitor here and just repeat the same test at 250 volts again. So set the meter onto 250, it's already switched on. You can see that the capacitor's charging, so we're at 100. Okay, so we've gone for infinite. So I think this meter reads up to about 1 gigohm. So this has actually exceeded 1 gigohm. Got to be a bit careful now because this capacitor has got 250 volts across it. So let's turn that off. Better just short that out, probably go with a bit of a crack. There we go, discharge that. Charging. clear. No, not a sausage. We saw in last week's video that the output voltage from this transformer, when the secondary was unloaded, it was about 185 volts. And the 185 volts that we measured was of course an RMS voltage. Well, this capacitor here, this will actually see the peak voltage across its terminals when it's in circuit. So we take out 185 and we multiply it by 1.4 and that gives you 260 volts. So when this capacitor was in circuit, it would actually see a maximum of about 260 volts across it. Now, I didn't want to risk damaging our transformer, but I would quite like to see what happens if we do put 260 volts across our capacitor here. So we've gone ahead and I've got our DC power supply, and I think what we'll do is we'll just wind up the voltage and see if anything explodes. Now, interestingly, I can already see that the current meter, it's given an indication. So we've got 100 volts there, not quite, turn it up a bit more. 100 volts, and we've got about, well, I think just over about 30 milliamps there. So this capacitor, it's passing 30 milliamps of current. Well, it shouldn't be passing any DC, so we can really see that this capacitor is failing. I suspect that it will probably start to get hot at some point. Let's keep going with the voltage. And I don't really dare go much higher. Oh, we can actually see the capacitor's breaking down because it's starting to pass more and more current. We're going to have to turn our voltage down a bit. So if we'd have connected this in our circuit, it probably would have ended up destroying our transformer. We're going to have to turn the voltage down. So we take 50 milliamps and times it by 100 volts. That actually gives us a dissipation within the capacitor of 7.5 watts. So unsurprisingly, this capacitor is actually starting to get quite warm now. It's getting hot, in fact. And the capacitor is definitely deforming in shape now. It was kind of quite a tight rectangular shape, and it's kind of bulging, and the edges are going rounded as the wax melts. It's all just kind of falling apart. Now I can see a lot of wax is clearly bubbling up on top. I'm actually having to turn the voltage down a little bit because unfortunately my power supply, it could be damaged if we run too much output from it. So it was nearly 100 milliamps there, but we're going into this cascade failure now. Even though I'm turning the voltage down, the current is continuing to just creep up and creep up. So we're going into a failure mode. Unfortunately, I don't think our capacitor's got the decency to explode live on camera, but certainly if it had been installed in our battery eliminator, it wouldn't have lasted long, and when it did go short circuit, it probably would have destroyed the transformer as well. So this is a living and dying example of why we need to change out some of these old capacitors in vintage radios. Although I've tried to put a screwdriver in it and turn it, that didn't work. So again, I think we're going to be forced with having to drill this out, which is always a bit of a perilous exercise. Well, as you can see, I've gone ahead and I've set up the knobbing in the milling machine, and we're going to try and attack it with a left-handed drill. It never works, but we're going to have a go at that first. Hopefully you can see the left-handed drill didn't actually work, but then again, didn't really expect it to. So let's go ahead and just drill it out. And because I'm using a small drill, we're going to engage warp speed 9. Okay, we've hit brass, so we've gone all the way through there. Everyone loves a winner. And I'll be the first one to admit, more by luck than judgment, we don't seem to have done any damage to the end of our potentiometer shaft. Just put a little dimple in it where the drills hit it. And there's our knobbage, which has been duly removed. So that didn't put up too much of a struggle in the end, did it? Following the denobulation, I think I will just go ahead and test this potentiometer one more time, because I wasn't getting a reading on it at all before. No, well, it is definitely measuring open circuit, so I think the only thing we can do is actually have to take this apart. For reasons, it does appear to have this little split pin which goes through the knob control, so again we'll just have to take that off. Well, I'm sure that you'll agree that this is actually quite an unusual looking potentiometer. I've certainly never seen one that's a triangular shape like this, and it's held together with these 3 screws. But if we turn it over and have a look at the back side, the screws are quite interesting in that they're designed to be wire sealed. And now I'm not sure if they were designed to be wire sealed to stop vibration, or maybe that these were a calibrated item. I'm not exactly sure. And what I mean by wired seals is, if you see the screw here, I can actually put this component leg through it like this. So the idea was you would get a piece of wire. When you put the nut down and tighten it up, you'd put a piece of wire and then twist it together, and then the nut couldn't actually come off. So that could be done for 2 reasons. It could, well, a few reasons. It could be done to stop people tampering with it. It could be done because it's a calibrated item, or it could be done because this potentiometer was designed to go somewhere with vibration and they didn't want the nut to come loose and fall off. So I'm not sure what the reason was. I've just noted another odd thing about this potentiometer. You can see that it's actually got a wire here soldered onto one of these screws. Now this is a screw which is actually holding the body together. So I'm guessing that the whole body of this would actually be live with HT voltage, which strikes me as really being quite dangerous, because this side either had just a rectified DC on it, or it had the resistive end of the rectified DC. But whatever wire it was connected to, certainly it had more than 150 volts on it. So that would mean that the case here had 150 volts on it, which wouldn't be good. The shaft here would have 150 volts on it, I'm guessing. I was going to say also that would put 150 volts on the case, but it wouldn't, because I've just noticed on the front panel here, can you see this black thing? Well, that's actually, if I can get it out, that's an insulating washer. So it looks as though this was insulated from the front panel by, it had a plastic washer on the back, then it had an insulating bush that went through the hole, and then it had another insulating washer on the front. So it was actually insulated from the main body, but certainly this control would have been live. So again, you know, they were brave back in the day. So if this knob falls off and you decided just to grab hold of this to adjust it, potentially you were in for a nasty surprise, weren't you? So I'm quite interested to see what's in here. Certainly I bet this is the first time this has been opened in at least 80 years. Ah, okay. That is really interesting. I kind of guess how this operates, but I've never seen one like this. I think you might call it something like a graphite pile. So what you've got in here, you've got some powdered graphite, just some powder here, which I can distribute. And the way that this works is, the way you actually change the output voltage is you actually screw this lever in, and that this plunger moves forward and it compresses the graphite powder together, and the more that it compresses the graphite powder, the lower the resistance will be. So I'm just actually wondering if the reason that I wasn't measuring anything on my own meter before is because probably the breakdown voltage of this graphite powder, the breakdown voltage is probably so high we weren't actually able to get a conductive path through it. I suspect that's exactly what it was. So certainly I have never seen a potentiometer like this before. I wonder what the name of this is for a graphite powder control like this. It reminds me of the inside of an Etch-a-Sketch if you ever broke one of them open as a kid. Wish I hadn't decided to fluff that up, because it's actually going everywhere now. Now this also reminds me of one of those old telephone microphones. I used to think were they called carbon powder or graphite powder? I forget what it was, but similar idea. When you compressed the powder, it would actually modulate the current flowing through the device, and that would change your voice into electricity. So this is a similar idea, that the way we reduce the resistance of this potentiometer is by screwing it in, because we did notice that this pad here, it moves forwards and backwards. If I screw it in, it moves back. If I screw it the other way, it moves out. So it's compressing this graphite powder. I've never seen anything like that before. That's real unusual. So I assume that one of the reasons that these screws did have provision for fitting a wire seal was just to stop some idiot coming along in 80 years' time and dismantling it and getting the powder all over the bench and themselves and the carpet and the cat and everything else. Yeah. Well, I think the best thing that I can actually do with this is put it back together. Because this thing really does have the potential to cause an awful lot of mess. I guess I'm lucky that when I opened it up I didn't have it upside down, because that would have got very messy very quickly, wouldn't it? So I suspect the reason that our ohm meter didn't work on this is because there's probably some form of breakdown voltage to actually get some conduction across that graphite powder. So I suspect it does need maybe a few hundred volts across it. So I think maybe that's what we should find out. So next time your wife asks you why you need to buy one more digital voltmeter, you can explain that there are reasons. I've gone ahead and I've just temporarily reassembled our graphite rear stack control into the front of the enclosure here, mainly because, as we saw, it has potential to have high voltages on the external casing, so I don't want to touch them. And of course making sure that we have refitted some knobbage, and again I've just put a temporary knobbage on it because the old one still needs a new grub screw. So I've got some meters on the bench. So we've got this meter here, so this one is going to measure the voltage across the rear stack. We've got another meter here, this one is set to measure the current through our load, and we're using the same load as we had last time, so this should give us, I don't know, something in the region of 20 milliamps when it's got 170 volts across it. Then we've got another meter here which is set on the volts range, and that's measuring the voltage across our load. So at the moment our potentiometer is screwed out, it's fully screwed out, so there is no compression on that graphite material, so we shouldn't actually be getting any current flowing at the moment. And I'm also using this high voltage DC power supply, and this is taking the place of our transformer, our rectifier, and in fact the capacitor as well. And as we calculated earlier, the maximum supply that we could see across our capacitor was about 260 volts. So again, I've gone ahead and I've wound up the voltage of our power supply here to create 260 volts, so that's the output at the moment. In fact, that must be a little bit high because I can see 266. Let's just wind this one down a little bit. 260.9, near enough. I'm going to start adjusting our rear stack control in a clockwise direction, and this is going to start to crush that graphite material. And as we start to crush this graphite material, it's going to push it together, and as we push it together, the resistance of it should fall, or that's the plan. Now we measured this with the ohm meter before, it didn't actually do anything, it was just open circuit, but I actually think that it just needs some high voltage across it to make it work. Okay, so I'm starting to tighten that up now, and I can feel a little bit of pressure, so we must be starting to compress the graphite material now. Oh, and I can see that on our meter here we've got about 2.4 volts, so we've adjusted 2.4 volts across our load resistor, and we've got 0.5 milliamps and 4 volts. Let's see if we can actually adjust this to a setting such as, let's see if we can adjust it to 10 volts, because you'd think it would be very crude because all we're doing is just crushing powder. Can't set an exact voltage, but more or less 10 volts, that would have been good enough back in the day. Let's try and increase the control. It is actually tightening up. This is a bit like screwing up a G-clamp, because you know when you tighten up a G-clamp on a piece of wood, when you first touch the piece of wood it's very easy to turn the G-clamp, isn't it? But as you start to put pressure on it, the handle gets harder to turn. That's what's happening to this. I'm actually finding this quite difficult to turn now. So it's getting a little bit tight, but we can see our voltage has risen to 57 volts across our load, and we're now passing 7 milliamps. Let's keep going. Let's see if I can set, I don't know, let's see if I can set something like 70 volts. So it does appear that the voltage adjustment using this rear stack control, it's actually better than I thought it would be. But you've got to remember though that this isn't actually a regulated power supply, we're just varying the resistance. So the operator acts as the regulator, he has to adjust this control to get the right voltage for the current that his radio receiver was actually drawing back in the day. So again, yeah, 73 volts, 9 milliamps. Again, so the first point that I think we'd really want to get to is for a battery set, we want to try to get about 90 volts on our battery set. So I'm going to screw this a bit tighter, and it is getting hard to turn now. So we're at 85 volts and 10 milliamps. Can we get to 90? Well, I've overshot very slightly. We're about 91 volts at the moment. It is climbing up. It's flicking around between 91, 92 volts. So yeah, not bad. That would have been quite good enough. Can we go a bit higher? Okay, so we've actually got up now to 130 volts. Now that was actually the rated output voltage for this device. So we've got 130 volt across our load here, and our load at the moment is drawing 16.6 milliamps. So our graphite rheostat, it's actually acting as a voltage regulator. So what it's actually doing is, it's actually regulating the voltage from, we've got 260 volts coming out of the power supply, and it's reducing that to 138. So we can actually work out what resistance value we've got set here. So if we take the voltage across the rheostat, which is 120 volts, and we divide that by the current flowing through it, which is 17 milliamps, that's going to come out at around 7,000. So we've got a resistance of about 7,000 at the moment. So let's just work out what power we are dissipating in our rheostat. So we've got 120 volts and a current of 17 milliamps. So we'll take our calculator and we'll do 120, and we'll multiply that by 0.017 for 17 milliamps, and that equals 2 watts. So again, we're actually dissipating 2 watts. Now, just looking at the size of our rheostat, it's physically quite big, and I don't think it would have any problems at all dissipating that 2 watts of power. Let me just switch off the power. So our rheostat control, actually I thought it would be warmer than that, but it's actually running pretty cold. Maybe it's heat sinking slightly into the front panel, but I estimate this is somewhere between 30 and 35 degrees. It's not actually much above body temperature, it's just slightly warm. So certainly this rheostat had no problems handling the type of loads which it were expected to connect to it. Now, having thought about it, I think the reason that they went for this type of graphite control rather than a more conventional carbon track or even a wire wound resistor which you would expect to see in power applications, the reason that they've actually done this is because to make something like a wire wound resistor, you need quite a long length of wire to make a resistance of about 7 kilo, and it would have been quite difficult for them to make. I have to say, I really am quite surprised at how well this compressed graphite control actually works. But again, the only thing to bear in mind is the actual operator acts as a regulator, so this isn't a regulator. You actually have to adjust this to achieve the voltage that you want, and if the mains voltage went up or the current consumed by your wireless set went down, the terminal voltage would go up, so you would have to manually just turn it down a bit. So it was a very manual procedure, but you know, you didn't need great accuracies of voltage. It probably wouldn't have made any difference to the operation of the radio, probably to within 20 or 30 volts. It was probably quite good enough, but we actually saw that we could adjust this within just a couple of volts. So yeah, I'm impressed with this early 1920s technology. I think we'll finish today's video where we first began in part 1 by taking a closer look at our Westinghouse copper oxide rectifier. I think to put our copper oxide rectifier in the proper context, a little history is essential. By 1920 the idea of rectifiers was nothing new, and an early form of point contact diode could be easily constructed using a galena crystal, better known as a cat's whisker. These were used with excellent results as detectors in crystal wireless sets. However popular as these were, they were only suitable for small signal use and they could not be used in power applications. Vacuum tube rectifiers, more commonly known as fermiomic diodes, were also in common use, and whilst these were superbly able to handle high voltages, they could not work at high currents and low voltages due to their internal high resistance. Mercury vapor rectifiers were also in common use, and these could be used at high currents and at lower voltages, but the operating requirements could be complicated and something simpler and perhaps more portable was required. Probably the most popular type of power rectifier around at the time was known as the wet type, and this consisted of an aluminium and a lead plate that was submerged in a solution of borax. They were frequently used as rectifiers for battery chargers, and they could handle relatively high currents and low voltages, but unfortunately they were not ideal devices as the wet solution could slosh around, and they were also prone to boiling off the solution. Now, although the wet type rectifier is long gone, their direct descendants are still with us in the form of the ubiquitous aluminium electrolytic capacitor. So our metal rectifier here is actually an early type of semiconductor rectifier, in which the semiconductor is the copper oxide, or in some cases selenium. And by the end of the 1920s, these metal rectifiers were readily used in power applications to convert alternating current to direct current in devices such as radios and battery chargers. The inventor of the copper oxide rectifier appears to have been a Mr. Lars Ola Grondal, who was working at the time for the Union Switch and Signalling Company. And you can find a description of this new type of rectifier in the Physics Review of the 27th of January 1926. The copper oxide rectifier we have on the bench here was manufactured by the Westinghouse Electric company, and they're a major manufacturer of rectifiers since the 1920s, often under the trade name of Westector. Now, there are actually several different types of metal rectifiers using different materials. Now, one of the most popular ones that you'll have heard of was the selenium rectifiers. Now, the selenium rectifiers were generally more efficient than the copper oxide types, and they could handle higher voltage. However, considerably more skill was required for their construction, and this made them unreliable, so in the 1920s the copper oxide rectifier was still ruling supreme. So let's take a close look at our copper oxide rectifier. Now, I'm hoping you can see that this rectifier is actually made up of a number of separate discs of copper, and if you count them, I think there's just over 80 in total, something around that number. And each one of our 80 discs is a rectifier in its own right, so it is equivalent to our little diode here, although not quite. So the way that these copper oxide rectifiers were manufactured, you'd actually start off with a disc of copper. Now, I don't have any discs of copper here, so we're just going to have to imagine that these are copper discs. So these were copper discs, and what you do, you'd take the copper disc and you would put it into an oven at a very specific temperature. You would heat it up, and that oven would be an oxygen-rich environment. And what you'd find on both sides of the copper disc, you'll get a very thin layer of oxide forming, and it's that oxide layer that works as a semiconductor rectifier. After removing the copper washer with its oxide layers from the oven, what they would then do is they would actually clean off one side of the washer. So one side would have a layer of copper oxide on it, which I've coloured black, and the opposite side would just be bright copper. But unfortunately the layer of copper would be very thin and vulnerable, so they would actually plate another electrode on top of the copper oxide, and they used to do that using a process called splutter coating. And then as part of the assembly process, what they would actually do is they would take a long steel threaded bar, which you can actually see sticking out of both ends here, and they would insulate that. I'm going to put some tape around here, but they would obviously have used something like a porcelain insulator. So this piece of tape is just representing our porcelain insulator, because without it our copper disc would just short out along the length of the steel bar here. So all they would do then is to take these discs like this, and they would just thread them onto this insulated bar. So you can now see we've actually got a stack of these little rectifier discs together. And then at each end of the rectifier here, you can see they've actually just added a couple of terminals, and these are just, again, flat copper discs which actually make contact with the stack of diodes here. So the construction of this is really quite simple, and actually some of the early radio pioneers, they did actually manufacture their own copper oxide rectifiers at home, so that couldn't have been an easy process. Now, I did say a few moments ago that each one of our copper discs with its oxide layer on it, I said it was equivalent to a diode. So why did they need so many of them? Well, the problem is they weren't very good diodes. These diodes actually work very well in the forward direction, but you would actually find that if you put a reverse voltage across it, so when the positive side of the AC waveform was coming into the rectifier, that was fine. But the problem was when the reverse direction, the negative voltage came in, these discs, they would break down, they would stop working, and they would fail. So because these rectifier discs, they used to break down at quite a low voltage, I think it was around 6 to 10 volts. So if you just had one rectifier diode and maybe 150 volts in reverse across it, this would just break down. So what they had to do is they had to stack many of these discs together to overcome this problem of the rectifiers breaking down. Now in the case of the rectifier used in our battery eliminator, I think you'll probably remember, offload it was being fed with about 180 volts of AC. But remember that that AC voltage, that 180 volts, that's an RMS measurement. So the actual peak voltage would be nearer to, I don't know, nearer to 250 volts or so. And at the opposite end of our rectifier, we would have half-wave rectified DC, because this is only a half-wave rectifier. It's just the equivalent of one big diode. And this capacitor is going to approximately charge up to what the peak voltage of the transformer is. So again, we're going to call that 252 volts. But the problem that you have with any type of rectifier circuit that's being fed from AC like this is, this end of the capacitor, that'll get charged up to plus 152 volts. So we've got 152 volts at this point of the circuit. Now, when we're on the positive half of the cycle, we've also got 252 volts at this end of the rectifier, which is kind of all fine and good. But the problem is, when the transformer is on the negative, the upside down part of the waveform, if you like, we're actually now got minus 252 volts on here. So the voltage across the rectifier, it's just over 500 volts. So each one of these little copper discs would have no chance of standing 500 volts on its own. So we had to stack so many of them together, over 80 of them, just to overcome this breakdown voltage. Well, I don't know about you, but I think I've done more than enough yakking for one video. But before we finish today, I'd really like to try and wake our rectifier up from its 91 years of slumber, because I'd be really interested to see how it operates. We're going to provide an AC source to our rectifier in the form of this variac, and we're going to measure the current using the flute meter. And we've got the copper oxide rectifier connected to a scope via two probes. So the first probe here on the right, this one is looking at the incoming voltage, so that's the raw AC. And the second probe here should show us the rectified half-wave DC. And to complete the circuit, we need some load on the rectifier, so we've got approximately 9 kiloohms of load here. So let's engage the warp engines, wind up the voltage, and see if we can wake up our rectifier after 91 years of slumber. Wow, can you see that? So we're actually getting some half-wave rectified DC on the output of our rectifier now, but it is quite a long way below the AC input. Let's wind it up. Now I can't actually take this to the full voltage because unfortunately with this scope probe combination we can only go up to about 200 volts. In real life we would be somewhat higher. So we have wound the voltage up as far as I can go at the moment, so that gives us an RMS input of 144 volts, and I've also got it to show the max, the top of the waveform here, so that gives us a 200 volt peak. Now you can actually see a similar thing for the actual rectified DC, so you can see that the rectifier here shown in blue, this is conducting on the positive half cycle of the main cycle, but it isn't conducting on the minus side. That is what we would expect for a rectifier, but we can see quite a difference between the peak of the AC mains and actually the peak of the DC output. Now if I actually just look at that, I've got it set up here, so I've got 200 volts peak on the mains and we've got 172 volts peak on the DC out. So if we take the peak of our AC supply, which we've said is 200 volts, and we take away the actual output DC, which is 172 volts, that's going to give us a voltage which is being dropped across our rectifier. And that's 28 volts. So of course 28 volts is pretty lousy compared with a modern diode here, which typically might be dropping about 0.6 of a volt. So yeah, in some ways it's not a very good rectifier, is it? But remember, we've actually got more than one rectifier here. We've actually got a stack of them, and actually all the forward voltages are adding up together. Now I think there was about 80 discs there, 80 rectifier discs, so if I just divide that 28 by 80, that should give us the forward voltage for each of those rectifier diodes. So let's just try that. And that gives us a number of 0.35 volts. So it looks like the forward drop of each of these copper oxide rectifier diodes, it's about 0.3. So actually our 0.35 volts, our forward voltage for our copper oxide rectifier, it's actually better than a modern silicon diode. But of course the problem is we actually have to stack 80 of them together to make a rectifier that will withstand the peak reverse voltage. So in some ways, to have such a big forward voltage will make this rectifier, not as efficient as it could be. And I did wonder if our rectifier was going to get warm to the touch, but no, it is actually still completely cold at the moment. But it appears to me that our copper oxide rectifier is actually working quite well. I do wonder if our silicon diode will work as well in 91 years. Leave it in the comments. As always, thanks very much for watching, and until next time, bye bye for now.